Greetings, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And I again thank the NASA Engineering and Safety Center, NESC, and Dr. Curtis Larson for making this series of webinars possible. So in the last couple webinar units, we've been discussing shock response spectrum. And a given time history has a unique shock response spectrum. But the converse is not true. So in other words, given a shock response spectrum, there are multiple types of waveforms that can satisfy that SRS within some reasonable tolerance bands. And that actually gives quite a bit of flexibility to our testing. So a way to think of this is that the SRS specification method is really an indirect way of specifying a shock test. So let's say, for example, that some field shock event is measured, and then it's enveloped using an SRS curve, perhaps with some statistical uncertainty margin added. Then that turns into an SRS spec. So then the customer takes that SRS spec as well as the test article into a test lab for the shock test. Well, the test conductor does not have to reproduce the actual field shock event, which might be impossible to do anyways, given practical limitations, but rather he or she can synthesize a different sort of waveform that will still satisfy the SRS and therefore meet the specification. Now, there are some caveats with that. Some people are concerned, and justifiably so, that if we use a different type of time history waveform, that is really not representative of the field shock, even though the SRS is satisfied. And people can become concerned, for example, about linearity and whether the test item is really a multi-degree of freedom system. And my quick answer to that is that up in an upcoming webinar, we'll address some of those. There's actually another type of a shock and vibration test. It's called time waveform replication, and that's a case where the idea is to actually replicate the field shock or vibration time history in the test lab. But let's save that for a future webinar. So today we're going to just assume that we can take our SRS spec and come up with any type of reasonable waveform we can to satisfy it. And we actually have two different methods for doing this. One is wavelets and two is damped sinusoids. And actually the second method also includes the wavelet method, but more about that later on. In fact, I think I'm going to take this unit 27 and divide it into two parts, because the two parts are each somewhat lengthy. I think that might make the most sense. So we'll call this Part A, and this will cover wavelets. So please also download and view Part B, which will be the damped sinusoids. Okay, so continuing on. So well, first of all, when we talk about wavelets, you may be familiar with the type of wavelet that I will call the cousin to the Fourier transform. Well, this is not a cousin to the Fourier transform. This is a more brute force basic type of wavelet that's a shaker shock wavelet. And the goal of wavelet synthesis is to synthesize an acceleration time history that can either be used for a shaker test or for a numerical simulation of a shaker test. So here's a small satellite payload, and it's attached to a slip table, which is driven by an electromagnetic shaker. And I don't really have the background of what that particular payload is, or even what kind of shock and vibration testing it may have been subjected to. But let's just sort of assume that it was subjected to a shock test. Now, a shock test may be performed on a shaker table if the shaker's frequency and amplitude capabilities are sufficient. And anytime we can do a shock test on a shaker table, that's a good day, because this type of shock testing tends to be more repeatable than other types of methods. But there are some limitations. It's only good for some either benign to moderate shocks, and certainly not for pyrotechnic shock simulation. So if we're going to do this shaker shock approach, we need a time history to satisfy the SRS. And there's at least two different candidate methods. I'll just mention two. We could use damped sinusoids or wavelets. Now, one of the requirements, regardless, is that the net velocity of our drive signal, the corresponding velocity to the drive signal, must have a net value of 0. And I'm going to say that the net displacement must also be 0. Well, in reality, we could tolerate a slight net displacement as long as the shaker table could recenter itself thereafter. But just for simplicity, let's say that the net velocity and net displacement must each be 0. So that's the requirement for our time history synthesis, regardless of what type of waveforms we use. So what we're going to do is we're going to synthesize a series of wavelets to satisfy an SRS specification for shaker shock. And this will become more apparent as we go on how we're going to go about doing that. Now, the neat thing about wavelets, they are intentionally and purposely derived so that each individual wavelet will have 0 net displacement and 0 net velocity. And the neat thing about that is that thus, if we have a series of wavelets, that series also has 0 net displacement and 0 net velocity. And that's very important for shaker shock testing. If we had a series of damped sinusoids, we would not meet those requirements just with that series, so we would have to also apply what's called a compensation pulse. And that gets kind of messy, and for a variety of reasons which will become more apparent, the wavelets are really the way to go. So what we're going to assume now is that our shock control computer will either do one of the following two things. So it'll either accept an ASCII text time history file, which will be the series of wavelets, or as an alternative, it will accept a wavelet table. So with some control computers, you can actually go in and tweak all the parameters in the wavelet table, and that would be another way of doing this application. Of course, the control computer most likely has its own built-in way of synthesizing a pulse, probably using wavelets. But it's kind of fun and interesting and insightful to do this just in our office computers prior to the test. And another thing that we really run up against is we have to remember that with a shaker system, particularly for shock, there are definite limitations. There is the stroke limit or the displacement limit. That's particularly critical if we have a lot of energy at low frequencies. Velocity is a limit. Acceleration is a limit. Force pounds is another limit. And then we could also talk about current and voltage and even temperatures all being limitations for a shaker test system. So a lot of times we're kind of just on the edge of, we have a specification that's on the edge of what a shaker shock system, test system could do. So we really have to be careful about coming up with a wavelet series that will fit within those parameters that I previously mentioned. Okay, so I think we talked about that slide already. So here's the wavelet equation, and really it's a lot more simple than it might look just off the bat. So this would just be for an individual wavelet. We'll say W sub m is the acceleration at time t for wavelet m. Then we have an acceleration amplitude A sub n. And here we have two sine functions. And really what this is, the second of the two sine functions is really the main sinusoidal oscillation. And it's 2 pi f sub m, that's the frequency of the wavelet. Then we have in parentheses, we have t, that's the independent variable time. And then we have t sub dm. Well, this is a delay time. So what we're actually going to do with these series of wavelets is we're going to have them staggered with some delay. Now this first sine term that we skipped over, this modulates the amplitude of the second sine function. And it has the same argument inside the brackets as the second one, except that in this denominator here we have n sub m. And n sub m is what's called the number of half signs, and it's an odd integer greater than or equal to 3. And again, this equation is purposely configured so that as we integrate to velocity and then double integrate to displacement, that all of the three amplitude metrics will each have a final value of 0. So the final acceleration is going to be 0, the final velocity is going to be 0, the final displacement is going to be 0. Then this wavelet is defined over a particular duration, so starting at the delay time and then up to the delay time plus this term here where we have the number of half signs divided by twice the nominal frequency of that wavelet. So this is the equation, and just looking at this equation you might not be able to really figure out offhand what it really means, but if we do an example it becomes so much more clear. So this is, I'm going to call this just a typical wavelet. It's just a single wavelet and its acceleration g versus time in seconds. And you can see there's an offset here or delay of 12 milliseconds. Then the frequency is 74.6 hertz. And here we have, if we count the number of positive and negative peaks, altogether there are 9. So we call this the number of half signs. So again, this has to be an odd integer greater than or equal to 3. So this is our 9 half sign wavelet with its other corresponding parameters. And I forgot to call out the amplitude, but it looks like about maybe 32 or so G there for the peak amplitude. So again, the idea is that we take a whole series of these wavelets with staggered offsets, and each individual wavelet can have its own amplitude, its own frequency, its own number of half signs, and obviously its own delay as well. And we just sort of kind of mix and match these so we can satisfy our shock response spectrum specification. But actually there's another consideration as well, is that for our case here, satisfying the SRS it's the primary goal, but it's not the only goal, because we want to get the most bang for the buck. So what we want to do with shaker shock testing is use the least amount of energy so that we can still satisfy that specification. So that means we want to come up with a base acceleration input signal that has the least possible acceleration, the least possible velocity, and the least possible displacement, all within some reasonable duration. So it's not just a process of synthesis, it's also a process of optimization. So let's take a particular specification here, and this is actually a published specification from Mill Standard 810E, and before you dash off any emails to me, I realize that this Mill Standard is up to Rev G or almost H or whatever, but I think this one is in the most recent revs as well, so let's just go with it. It's called the crash hazard for ground equipment. And we have SRS Q is equal to 10 with the 3 natural frequencies and the corresponding peak accelerations for each of the 3 natural frequencies. So this could be, I guess, maybe there's a radio that's mounted in a military truck or a Jeep or a Humvee, and that Humvee is going over washboard roads and rough terrain, and there's a possibility of a crash, and in the event of a crash, the radio needs to remain functional. So let's just go ahead and go with this, and we're going to synthesize a series of wavelets as a base input time history. And as I mentioned, we have multiple goals here. Of course, we want to satisfy the SRS specification within some reasonable tolerance bands. But we also want to minimize the displacement, velocity, and acceleration of that base input. So let's go to our MATLAB. We call up our MATLAB here. And we're going to go to our vibration data GUI package, and we're going to do something new today. with the GUI package. Well, the first thing we want to do is copy and paste these breakpoints, or you can call them coordinate points. And I'm just going to copy and paste them and put them into the MATLAB workspace. Now, if you know a better way of calling in the data to MATLAB, that's great. You should use your own way. Another thing we could have done is we could have copied and pasted these into like a Word document or some text file, and then we could have called that text file into MATLAB as well. So that's another way. But this way I think is as good as any way. So let's go to vibration data, the GUI package. Take a moment to come up. MATLAB's a little slow. Okay, this week we're up to version 6.2 and rising. So in this case, we're going to have a shock response spectrum. It'll be acceleration. And we're going to use the wavelet synthesis option. Let's click on begin. Okay, so this is vibration data underscore wavelet underscore synth.m. This script synthesizes a time history to satisfy an SRS specification using a wavelet series. And we already have our array preloaded into MATLAB. We'll just call that SRS underscore spec. And our next step is to read in that data. Okay, there's a whole bunch of parameters that we need to go over. One is the number of trials. So this is the number of candidate waveform series that we're going to come up with. And if we were doing this in earnest, I might set that at 1,000 or 2,000. But just for webinar purposes, I'm only going to put in 75 just to make this exercise go a little quicker. The sample rate. Now, our highest natural frequency is 2,000 hertz. So our sample rate should be at least 10 times that. So let's go ahead and we will put in 10 times that. So we have 20,000 samples per second, or you could say 20,000 hertz if you like. We can either limit the time history points or set the duration. And let's set duration. And now the way I set duration, and this may be a different emphasis than the mill standard, is what's our lowest natural frequency? Well, it's 10 hertz. One period of 10 hertz is 100 milliseconds. So I want to have at least two periods or two full cycles at 10 hertz, and maybe even just a little extra. So I'm going to say 0.24. That's 240 milliseconds. And that's just what I'm going to do. If you want to try something different, go ahead. There's a couple other parameters we kind of skipped over. Let's go ahead and use the 1/12 octave spacing. That's for the natural frequencies. We'll pick English units. Q is equal to 10. In our strategy, let's use approximate reverse sine sweep. Now, just through some logical reasoning as well as empirical experience, it turns out that it's in many cases it's best to do the high frequency wavelets first and then kind of sweep down to the low frequency wavelets. We'll go ahead and use that, and it's not an exact science, it's not a perfect process, but let's just go ahead and do that and see what we get. Optimization weights. Well, we have 5 parameters we're concerned with. We're concerned with what is the highest individual error. So that's the error with respect to the SRS of our synthesized time history relative to the specification SRS. So what's the highest error at any given natural frequency? Then there's a total error, peak displacement, peak velocity, peak acceleration. Now right now I have all these weights as 1, but these could be real numbers, they don't have to be integers. And if we were more concerned about displacement, then we could set displacement at 2 or 3 if that's what we needed to, if that was the critical parameter, for example. So again, of course, as usual, I want you to do this as a homework exercise, and certainly feel free to vary these parameters. If you have your own specification, you can put in your own specification and just play around and have fun with this. Well, let's go ahead and run this for our case here. So I'm going to, okay, intermediate results are written in command window. So let's go to the command window. And this is going to take, a minute or two, maybe 2 minutes. So what we're doing is going through all the different trials. Now I need to fill in some gaps and explain to you what's really going on. But you can see for each trial there's a peak acceleration, a peak velocity, a peak displacement, a total error, and the individual error. And these are all parameters we want to minimize. Okay, so while we're waiting for that to go, let's go back and fill in some gaps. And I want to go through what the software is doing. And this will just be an overview of what the software is doing. So let me see if I can go back to slideshow there. Okay, so there's our setup that we just did. So step 1, we generate a random amplitude, delay, and half sign number for each wavelet. Again, the number of half signs has to be odd integer greater than or equal to 3. And these parameters will form a wavelet table. So we do that for each natural frequency of interest, which in our case, for example, we're running this at 1/12 octave spacing. So then we synthesize an acceleration time history from the wavelet table. We use that equation I showed you a couple slides back. We then calculate the shock response spectrum of the synthesis. Now, what we're going to do is, we just finished our, we'll talk about these plots here in a couple, 2 or 3 minutes. Okay, so let's see. So we calculate the shock response spectrum for that synthesis trial, and then we compare it relative to the specification. And at this point, we're going to do some modifications on that given trial, that given candidate, because we're going to go back and try and scale those wavelets so that the synthesized SRS matches the specification SRS as closely as possible. So we're going to work within each wavelet to make it the best it can be, or I should say within each wavelet series, which of course is so it's both individual wavelets and a series that we're trying to make the best it can be and they can be. Got a little tongue-tied on that one. Okay, so then we generate a revised time history. We repeat steps 3 through 6 until the SRS error is minimized or an iteration limit is reached. So there's only so many times we can go back and rescale those wavelets, and eventually at some point the error will start increasing or diverging. So then we calculate the final shock response spectrum error for that given candidate, and we also calculate the peak acceleration values, and we integrate the signal to obtain the velocity and then again to obtain displacement. So we get our peak values for each of the 3 amplitude metrics. And then step 9 is we repeat steps 1 through 8 many times. Well, for the example that we're doing in class here, many times is equal to 75. But again, if you're doing this in earnest and you really have a tough spec that you're trying to meet, you might want to do it 2,000 times. And then we choose, what we do is we go through a kind of a ranking process to rank these waveforms in terms of their SRS error, the 2 error parameters, as well as the 3 amplitude metric parameters. So we go through a ranking process, and then we choose the one that gives us the best overall rank in terms of those parameters. And we are using those weighting factors as we make that selection. So let's go back and see what we have for our in-class exercise then for our wavelet synthesis. Okay, figure 1, I'm pulling it over from my second monitor. This is acceleration in g versus time in seconds. So this is a series of wavelets. And what we've tried to do is do the high frequency wavelets first and then gradually sweep downward to lower frequencies. Now, does this actually look like a crash hazard shock or any type of shock? Well, no. Is that a limitation for this whole testing methodology? Yes. But this, most of the time this works well enough. But if we are concerned about nonlinearities and multi-degree of freedom behavior and other things, there are other tools we can use, particularly if we need to replicate the recorded field waveform in the test lab. But But today we're saying we don't need time history replication. That's a topic for another day. So we're saying as long as we meet the SRS, that we're good to go, even though that's a funny looking shock pulse. Now, the final acceleration is 0. I'm going to pull over the integrated velocity. So velocity inches per second versus time in seconds. So this is somewhat oscillating about the 0 baseline. And the final velocity is equal to 0. That's important. We have displacements. Now, by the time we double integrate to displacement, displacements can be somewhat one-sided. But we just need to make sure that the peak displacement is within the stroke limit of the shaker system. And our final displacement is equal to 0. That's good news. Now here's a non-trivial plot here. This is our shock response spectrum. Q is equal to 10. So we have peak acceleration in G versus natural frequency in Hertz. There are 3 black lines. The middle black line is our nominal test spec. And then in this case I have plus and minus 3 dB tolerance bands, which is probably a typical bands for a shaker shock test, but if you have different tolerances you could apply those. And then we have the positive and negative curves. These are from the SRS of our synthesized acceleration time history. And you can see in this case both curves are well within our upper and lower tolerance bounds. So it looks like we're good to go for our shaker shock test. Before we make that final decision, let's go and take a look here. So in this case, the optimum of the 75 was case 57, and you can see it has a peak acceleration just below 20 Gs, peak velocity just within 33 inches per second, displacement less than 7/10 of an inch, and then the maximum error. So we would need to verify that these 3 parameters are suitable for the capabilities of our shaker test system. Having a peak displacement about of 0.671 inches is probably okay for most shaker systems, but we might want to be just a little extra careful on that and give ourselves a little extra margin. So again, if we were doing this in earnest, we might want to do 2,000 trials instead of 75, and maybe even bring that peak displacement down to, say, a ½ an inch peak. Okay, and let's see what we have here. So let's go back to our GUI. Let's go to our GUI package here, and let's just pick out a typical frequency, natural frequency. Let's see what happens at, say, 200 Hertz. So what we're going to do is take our synthesized acceleration time history. I'll just call it excel_syn, and we can save that to our MATLAB workspace. Now, if we want, we could also save the velocity corresponding to velocity. We could save the corresponding displacement, the corresponding SRS, and the wavelet table as well. In fact, let's go ahead and save the wavelet table. I'll just call it wave table. And our wave table has 4 columns. So let me go back to the our MATLAB package here. So I'm going to show you what a wavelet table looks like. Okay, I made a mistake. Let's try this again. Wavelet table. I needed to go back to the list box and correct that. Okay, save wavelet table. Okay, one more time. I don't mind making mistakes because you might make some of the same ones. So we have 5 columns of numbers. Now, MATLAB kind of does a funny thing. It scales everything in this case by a factor of 1,000. But the first column is the natural frequency of the wavelet. The second column is the acceleration in G. And then for the third column, we have the frequency of the wavelet, and then the fourth column we have the number of half signs, and the fifth column is the delay time. And I want to. Okay, I made a mistake. I'm sorry. Let me start over. The first column is simply the wavelet number. Now, it's really an integer, but MATLAB is making it appear as a real number because of the funny way it does that, 1,000. So I'm correcting myself. So the first column is actually the wavelet number. The second column is the amplitude, acceleration in g. The third column is the natural frequency in hertz. The fourth column is the number of half signs. It's an odd integer greater than or equal to 3. And then the fourth column is the delay time. And it looks like the delays are all 0, but we have to remember that MATLAB is doing a funny thing here with that 1,000 factor. In fact, let's go and see if we can look at this table in a little more detail. So let's see if I can do this correct. So if I take the first row and all the entries, let me pick maybe the second row, or let's do a couple rows here. Okay, in this case we don't have that funny 1,000 factor anymore. This first column here is really meant to be an integer, and that's the wavelet number. Again, we have acceleration in g for the wavelet. Then we also have the frequency in hertz for the wavelet. We have 1/12 octave spacing, which means as we double the natural frequency, there's 12 steps. In fact, I can show you that a little bit better here if I. Okay, so as we go from 10 hertz to 20 hertz, there's 12 steps in there. And this column here, this fourth one, it's really an integer, but in order to put things in a wavelet table in MATLAB, we have to have everything be a real number. There's probably some other way of doing that you might know a better way. So this is the number of half signs, and then you can see the delays are not all equal to 0, although some are, but the various delays in seconds there. So we could export this as an ASCII text file, and then we could use that for future reference, or we could input these numbers into a vibration control computer that will accept a wavelet table, or will let us otherwise manually edit a wavelet table. Well, manually editing would be a real pain, but I'm sure I've done that before, way back when I worked in a test lab. Okay, so the next thing we want to do then is one of our favorite things, that we want to take this acceleration time history. Okay, there's the velocity. Let's go to figure 1. And we want to apply it as a base input to a spring mass system. So again, that's one of our favorite things to do. In fact, just to kind of remind you, let's go back to the slides here, the PowerPoint slides. So this happens to be the same one we just generated in class. This is our synthesized acceleration time history. It was case 57. And you can see off to the right the different metrics there characterizing that waveform. And then the corresponding velocity time history in inches per second versus time in seconds. The corresponding displacement, which in many cases will be the most important of all the parameters, because frequently we're running up against the stroke limit when we do shaker shock testing. And then the shock response spectrum, we've seen this plot before. We have good compliance to the nominal spec within the plus and minus 3 dB tolerance bands. So here we are now. We want to take that acceleration time history and apply it as a base input to a spring mass system, a single degree of freedom system. And we've talked about this system before. And of course, the next step would be we would draw up a free body diagram and use Newton's laws to sum the forces on the mass, and we would derive the governing equation of motion. And then for the case of an arbitrary input like we have, we would then use a convolution integral, which is inefficient to solve. So we would instead use a David O. Smallwood ramp invariant digital recursive filtering relationship. So let's go ahead and do that. And looks like I have a case called out for 400 hertz, Q is equal to 10. So let's keep this plot in mind here. This is our SRS, and what we have here is at 400 hertz we're into the plateau region, and we have 75 Gs. So let's go back to our MATLAB GUI here. So let me type in vibration data. Okay, in this case now we have an acceleration time history, and we're going to do single degree of freedom response to base input. Let's go to that option. We've done this before on many occasions. This is one of our favorite things to do in this class. And preloaded into MATLAB we have accel_syn. That's what I called that acceleration time history. We're going to run 400 hertz natural frequency. Q is equal to 10, what's equivalent to 5% damping. With our English units, let's calculate. We get our descriptive statistics here, and we find out that our peak positive and peak negative values are both approximately equal to 75 G. So that's all well and good, as it should be. So we have our couple of plots here. We've seen this before. This is our synthesized wavelet series to satisfy the SRS. It's kind of setting up somewhat like a reverse sine suite. So here's the acceleration response at 400 hertz, Q is equal to 10. So you can see the effects of some dynamic amplification going on. The peak here is less than 20 Gs, and the peak here is roughly 75 Gs. So the spring mass system is amplifying energy at its natural frequency. So this shows what's going on in the time domain for that particular oscillator, for its acceleration time history. And we might also be interested in the relative displacement time history for that same frequency and Q value. So we have relative displacement in inches versus time in seconds. So relative displacement could be important for a number of reasons. We're going to be later on in a future webinar talking about Steinberg's criteria for electronic components, and we're going to be looking at circuit board deflections. And in that case, relative displacement will become very important. And also there are times with an isolated component. Now, at 400 hertz, this is probably not an isolated component. Typically when we isolate components, we might have a natural frequency below 50 hertz. Of course, it depends on what the mass of the object is and other parameters. But still, we might be interested even at 400 hertz what the relative displacement is. There are possible concerns with stresses as well as things like optical alignment and sway space and clearance that would be affected by relative displacement. Again, that would be more critical at lower natural frequencies, probably not an issue at 400 hertz, but still this is an interesting plot to take a look at as well. And that's available to you as one of the tools in your toolbox. So we found out that at 400 hertz, our SDOF response was about 75 Gs, and that corresponds to these points here, the red curve and the blue curve. And you can see close to 75, they're about 75 Gs at 400 hertz. The red and blue curve are almost intersecting that black line at those two frequencies. So what the SRS, just as a reminder, what the SRS algorithm does is it does this single degree of freedom calculation for each of the family members. So for each natural frequency of interest, in this case spaced at 1/12 octave. And that's what it's doing. But then there's this data reduction process that goes on. So instead of retaining the whole response time history, the SRS instead just retains the peak positive and peak negative values for that given oscillator. And that becomes the SRS plot. So the SRS function takes care of all the bookkeeping for us. So that's just another little thing you can do there with your synthesized waveform. Oh, there's something else I wanted to mention too. Let's go back to our SRS synthesis here. So let's go to shock response spectrum, wavelet synthesis. And after we synthesized our waveform, oops, it's disappeared now. So I'm just going to go ahead and let's just do 10 trials here. I'm just going to do a trivial case, everything the same, because there's something else I wanted to show you. So just type in a few numbers here. So this is only 10 trials, so the results might not be that very good. Because I'm going back and showing you now something that I skipped over that I want to go back and mention. Okay, so you can see with only 10 trials, not quite as good compliance, but we're still within the tolerance bands. Displacement, peak displacement, rather one-sided, and it's up to about 0.85 inches. That might be a little too close to our limit for comfort there. And then the reverse sine sweep type. But what I wanted to show you, and I skipped over later, is we can also export that acceleration time history into a NASTran file. And then you could call in that NASTran file to, say, phi map, or you could bundle that NASTran file in the case control deck for a modal transient run for NASTran. So if we do that, we can, well, one thing we might want to do is we have acceleration in G's. For the purpose of NASTran, we might want to make that inches per second squared. So we might want to apply that scale factor. And then I'm just going to call this synth.nas. So let's see if I can call up that file here. Okay, I'm going to fumble around a little bit to get to where I have my MATLAB. And what I called it synth.nas. So here is a NASTran friendly file for that acceleration time history. So we have the time in seconds, acceleration G for each of the time history points, put in this table here that is compatible with NASTran. So then we could do our modal transient analysis. That's another thing we can do. Just sort of to summarize, we're about done with wavelets here. Wavelets are it's a very user-friendly format in terms of what a shock table can do. It tends to be a very robust method for performing these shaker shock tests. This wavelet series format very much lends itself to shaker shock testing, especially or among other reasons, because the final acceleration and the final velocity and final displacement will all be zero. And hopefully it's repeatable too. Anytime we're dealing with shaker shock systems, there's always the potential problems of fixture resonances and other things going on with that shaker test systems. But in many cases, this can be a very stable and just really good way to go for performing that shaker shock test. Okay, so I think that just about, I've got a couple more slides. So this is just what we did in class. So we went to our function vibration data underscore SDOF underscore base, which calculates the response of a single degree freedom system to base excitation. Then we applied our wavelet series, and we got an acceleration response of 400 Hertz. Q is equal to 10. And okay, then we also had our relative deflection plot, which I'm omitting. Okay, so our next unit that's going to be a separate recording is going to be on damped sine synthesis. So please check back for that. So we'll see you soon. We will see you soon. Thank you, and goodbye for now.